In this video, we're going to start looking at solubility equilibria. And the first thing I want to do is just review soluble versus insoluble ionic compounds. And if we wanted, instead of saying ionic compounds, we could just say salts. So soluble versus insoluble salts. So typically, if we just say the word soluble, we're talking about aqueous solution. So these guys are going to be ones that dissociate into ions in aqueous solution. When you learned these in either 150, 151, probably 130 also, or high school, we said that they are electrolytes. Right? Electrolytes were things that when we put them in water, we're going to form charged particles or ions. And we used our solubility rules to determine whether or not something was soluble or insoluble. Right? Our insoluble ionic compounds, and again, if you just want to say insoluble salts instead, that's fine, right? We would say that these do not dissociate into ions in aqueous solution. And we would have said that they were non-electrolytes, right? They're not going to form charged particles in water. In actuality, they do actually dissociate to a small extent. So in the past, we've probably just said they don't, but really about 5% or so does tend to dissociate. So these do actually dissociate to a small extent. And you don't need to memorize these numbers, but just kind of a guideline. If something is considered soluble, usually greater than 0.10 molar in solution, dissolves at room temperature. So RT for room temperature. Remember from your chemistry past, right? We can increase solubility by increasing the temperature. Kind of another way to look at that, we could say that greater than 1 gram dissolves per 100 milliliters. And again, this is at room temperature. If something is insoluble, kind of the cutoff for a small amount would be 0.001 molar. Again, at room temperature. So RT for room temperature, 25 degrees Celsius is considered room temperature. Maybe we should write it that way instead. Written another way, we could say less than 1 gram dissolves per 100 milliliter. So some of it is dissociating into ions, right? It's just not a very large amount, right? If I had 100 milliliters of solution, less than 1 gram of it is going to be in its ionic form. And again, we used our solubility rules to determine if an ionic compound is soluble or insoluble. And again, we're using the word insoluble, but we do mean slightly soluble. We could actually add that. These are going to be slightly soluble ionic compounds. So our insoluble ones, right, we're essentially saying, well, they're actually slightly soluble. A few examples, and you do have a copy of those solubility rules on the front of your periodic table. So if you want to pause real quick and grab your periodic table and then come back, I'm grabbing mine also. we'll go through some examples. So we're going to determine, are the following soluble or insoluble, and again by insoluble I mean slightly soluble, in aqueous solution. And my first one, we'll look at sodium carbonate. So again, if you haven't grabbed your solubility rules, please do that. We do need to remember how to determine whether or not something is soluble or not. And again, this should be reviewed. This goes back to your chemistry past. So I'm not going to really walk through the rules. We're just going to go through our examples. So hopefully you guys grabbed your periodic table. So what do you think? Soluble or insoluble? Good. Hopefully you said soluble. Rule number 1 on your periodic table says if it has a sodium ion in it, it is going to be soluble in aqueous solution. If we were to take sodium carbonate, right, aqueous, we put an AQ after it because it's soluble, I'm going to get sodium ions. Sodium has a +1 charge. I do have 2 of those, right? This 2 tells me there's 2 of them. And then carbonate, CO3 2-. You might have to review nomenclature a little bit, right? You won't need to be able to tell how many ions and your charge on those ions given a compound. So if you need to go back and look at that, please do. Carbonate is one of the polyatomic ions that you needed to have memorized in your previous class. So I do expect that you know that the charge on carbonate is a 2-. If I was to make a beaker drawing of these, right? Everyone loves beaker drawings. I'm not going to have sodium carbonate, right? What I'm going to have is I'm going to have 2 sodium ions and 1 carbonate ion, right? Because my arrow is only going in one direction. I put it in water, all of it separates. It's a strong electrolyte. Another example for us. Let's look at calcium chloride. So again, using your solubility rules, soluble or insoluble in aqueous solution. Hopefully you guys are coming up with soluble. This time I'm using rule number 3. It says if it has chloride ions in it, it is soluble. There are some exceptions to that. Those exceptions are silver, lead 2+, and then mercury 2+. So if you have silver, which has a +1 charge, lead 2 or mercury 2 ions combined with chloride, bromide, or iodide, it is insoluble. Calcium is not one of those cations, so it is soluble in aqueous solution. Again, right? If I had calcium chloride, I put an AQ after it because it's soluble. It's separating into calcium, which is going to lose 2 electrons when it forms an ion, and then 2 chloride ions. Again, both of those being aqueous. Right, my beaker drawing for this one, I have 1 calcium ion and I have 2 chloride ions. Another example for us, how about calcium fluoride, soluble or insoluble? So calcium fluoride is actually going to be insoluble, though I'm writing soluble, sorry about that. So I don't have a rule on my periodic table for calcium or fluoride. So this one is going to be insoluble, right? Chloride, bromide, and iodide are soluble anions with those 3 exceptions, but fluoride isn't on that list. So this one is actually going to be insoluble. And we can write equilibrium reactions for these. So I'm going to take my calcium fluoride. I'm going to put an S after it this time because it's solid, right? It's insoluble. Be really careful. If it's insoluble, it gets an S. If it's soluble, it gets an AQ. The S stands for solid, not soluble, so just be careful. Some of it though, right, we said it is slightly soluble. We're saying insoluble. Remember, it is actually slightly soluble. We've modified that a little bit. So I am going to get some calcium ions. Calcium still wants to lose 2 electrons when it forms an ion, and then 2 fluoride ions. And then this one does go back. If I was to draw my beaker drawing for this one, I'm going to have some calcium fluoride. I'm going to also have some calcium and 2 fluoride ions. And then proportionately, it's when I say slightly soluble, it's actually really not very soluble at all. So it's going to be a lot more calcium fluoride. It's going to be more of this one. Like this is not proportionate. It's not a 1-to-1, so much more. Right? If we wanted to draw 95 calcium fluorides, then I would draw about 5 of those calcium ions and twice that amount, right, fluoride ions. And I'm just guessing, but it's really much more calcium fluoride. So we do have both some of that solid and those ions in aqueous solution. So I want to look just a little bit more detail about this part. So because it does exist at equilibrium, we can write an equilibrium constant expression for this. So slightly soluble ionic compounds, right, just not to be too confusing, also known as insoluble, I keep writing that wrong, insoluble salts, are defined by an equilibrium constant, and it's called a solubility product constant. So it is an equilibrium constant, so capital K, that's a capital, and then SP for solubility product. And then remember, whenever we're writing our equilibrium constant expressions, it's always concentration of products over concentration of reactants raised to a power equal to their coefficient, excluding pure solids and liquids. So I'm just going to rewrite this example. Actually, I'm just going to copy it, this equation down below. And if you want to hit pause so you can rewrite it, so I strongly encourage that. And then its solubility product constant expression, right? My equilibrium constant expression is going to be the concentration of products raised to a power equal to its coefficient. We've been, with all of our acid and base reactions, it's always been a 1-to-1 ratio, right? Even if our acid was diprotic, we lost 1 proton at a time. So we haven't had to remember to raise our concentration to that power in a while. So watch out for that, right? I do have 2 fluoride ions, so I'm going to have my concentration of fluoride raised to the 2nd power. So don't forget, it's been since chapter 13 since we've done that. And then normally it would be over the concentration of our product, of our reactants, but because that reactant is a pure solid, it doesn't go there, right? We exclude them. And you don't even have to write this. You could just leave it off, and that would be our expression. I do have the value for us. I'm just grabbing it. I have it on some paper here. So if you hear crinkling of paper, it's me just trying to find it. And it's 3.5 times 10 to the negative 11th. Again, it does have units. In this case, it would be molar cubed, but you don't have to show them because it is my equilibrium constant. And I just want everyone to note that this is a small number. right? Remember, we can tell the extent of our reaction based on the value for our equilibrium constant, right? Since this is a very small number, it tells me that these concentrations are very small. So I don't have much here, I have much more over here, right? This would be reactant favored. If we go back up and look at our beaker drawing, much more of this one. So it's a small number, right? This would be a reactant favored reaction. So mostly the solid, right? Just a small amount, right? It's slightly soluble, a small amount of the ions. The value of our solubility product constant for KSP is determined at the saturation point, and that is probably important to note. Remember, a saturated solution is a solution that contains the maximum amount of dissolved solute. You can have a supersaturated solution. How would you get a supersaturated solution, right? Supersaturated would be larger than the maximum amount, which I know sounds weird, but how would one get a supersaturated solution? Yeah, you would heat it, right? We can increase solubility by heating it. So these are temperature dependent. And we should actually take this minute to define solubility, because we're going to need that too. We're going to actually calculate solubilities and use solubility to calculate our values for KSP and so on. So if I talk about the solubility of something, we're actually talking about the amount of dissolved solute. So the amount of, let's just say, solute that dissolves per unit volume of saturated solution. Again, a saturated solution is a solution that contains the maximum amount of solute per solvent or per solution, right? If it's unsaturated, it's less than the maximum. If it's supersaturated, it's more than the maximum. We get that by heating it up. And again, this is temperature dependent. So if a solubility is stated, it's standard, it's usually at standard state, which would be room temperature. So if I don't specify a temperature, we are assuming 25 degrees Celsius. So the amount of solute that dissolves per unit volume. So just like if I give it in molarity, my unit volume is a liter of solution. If I say grams per 100 milliliters, now my unit volume is 100 milliliters. So whatever it is that we're talking about. So let's do one more example. We're going to write the balanced equilibrium equation and equilibrium constant expression which I can't spell. For calcium phosphate. So again, if you need to go back and review nomenclature, please do that. I'm just going to write it here. So calcium phosphate is going to have this formula. If you use your solubility rules, you are going to find that it's insoluble. We now know that that means it's slightly soluble, but I still am going to put that S after it. This S is going to be important because when we write our equilibrium constant expression, it's not going to be included. So it is important to have that S there. And then it's going to dissociate into 3 calcium ions plus 2 phosphate ions. Again, phosphate was one of those polyatomic ions that you needed to have learned. So again, if you need to go back and review these, please do. It's important that you can write this, right? If I don't know that there's a 3 here and a 2 here, when I write my expression, I'm going to raise them to the wrong powers. So it's important to be able to take calcium phosphate, right? When I write it this way, know that this is what it looks like, and then be able to separate it into the ions, right? And the correct number of ions. Always check, this is a good check too. Your net charge should be the same on both sides. So here I have no charge, right? It's 0. Here I have 3 positively 2 charged ions. So that gives me a +6. Here I have 2 negatively 3 charged ions. So that gives me a -6. That +6 and -6 is equal to 0, right? Our number of positive charges, right, our +6 must equal our number of negative charges, a -6. So just a couple ways to check to make sure that you're not totally off base. Our equilibrium constant expression, so KSP is going to be the concentration of calcium ions. Because I have this 3 here, I'm going to raise it to the 3rd power, multiplied by the concentration of phosphate ions, and then I have a 2 here, so we're going to raise that to the 2nd power. Nothing on the bottom, right, because it's a pure solid, and solids are not included in my expression. If we know the solubility of our compound, we can actually use that to calculate our solubility product constant, right, the value for KSP. So we can use the solubility of the compound to calculate the solubility product constant, KSP. And the easiest way is to just go through an example. So we're going to calculate the solubility product constant for silver chromate. Again, if you need to review nomenclature, please do. Chromate is one of those polyatomic ions that you needed to have learned last semester or whenever you had 151. The solubility of silver chromate. Remember, silver is one of our fixed charge metals, is 6.50 times 10 to the -5th molar, right? So if I had 1 liter of solution, 6.50 times 10 to the -5th moles of it would be silver chromate. And we're going to start this problem just like what we were doing up above. I'm going to write my balanced equilibrium reaction equation, and then I'm going to set up my expression. And use a different color just so it sticks out a little bit. So using our solubility rules, this is solid. And it's going to separate into 2 silver ions and 1 chromate ion. And I'm going to leave a little bit of space here, so I'm just going to go down a little bit. My solubility product constant is going to be equal to the concentration of silver ions squared, right? I have 2 of them, multiplied by the concentration of chromate ions. So what we need to do is figure out what those concentrations are. And we're given the solubility of this, right? It's 6.5 times 10 to the -5th molar. And then according to our balanced chemical equation, right, for every one of these, right, there's a 1 here, I'm going to get 2 of these. So basically, if my concentration of this was 1 molar, my concentration of this would be 2 molar. If we were doing the plus and minus x stuff, if I subtracted x here, I would add 2x because there's 2 of them, right? For every 1 here, there's 2 of these. So what that means for us is that if our concentration, right, of silver chromate is 6.50 times 10 to the negative fifth molar, my concentration for silver is 2 times that number. Right? Whatever the concentration of this is twice that amount. So we're going to take 2 and multiply it by that to get the concentration. And then this one's a 1-to-1 ratio, right? There's a 1 there. So whatever the concentration of this one is the concentration of chromate. So this is 10 to the negative fifth, 6.50 times 10 to the negative fifth molar. So my concentration of silver ions, I'm just going to take 2 and multiply it by that. So when I do that, I get 1.30 times 10 to the negative fourth molar. And then this is my concentration of chromate. And then I can take those numbers and plug them into my expression. So KSP is going to be equal to 1.30 times 10 to the negative fourth. And then I still need to square it. Be really careful. This is the biggest mistake that I see. We have to multiply this number by 2 to get the concentration, right? The reason we're doing that is because of this 2, right? Whatever this concentration is twice that amount. So that's where this is coming from. I still have to square it though, because my expression says to square it. So we're taking the concentration, right, our solubility, we're multiplying it by 2, but then we're also squaring it because my expression says I have to square that concentration. So don't think just because you're using the 2 here, you're done with it. You still need to square it. So just be really careful for that. And then that's going to be multiplied by my concentration of chromate ions. And I did drop my units because when I solve, I'm going to leave my units off. I'm grabbing my calculator here. If you wanted them, that's fine. It would be molar cubed in this case, but you don't actually need them. So typing this into my calculator. Oop, I almost forgot to square it. Don't forget to square it. And then I just want to double check my answer here. And I get 1.10 times 10 to the negative 12th. So that would be my value for my solubility product constant. And again, I do expect small numbers. Remember, these are slightly soluble. I expect that it's going to be reactant favored, right? Most of it is going to be this. I expect that these numbers are going to be very, very small. So if you get a big number for your answer, you goofed up somewhere. Go back. It's going to be a small number. One more example of this type for us, but with just a little twist on it. Calcium fluoride has a gram solubility of 0.016 grams per liter. And we're going to calculate the solubility product constant again, KSP. Just making this neater here. All right. So again, remember, we're going to basically do the same thing. We're going to write our formula for calcium fluoride. I'm going to write my balanced equilibrium equation. I'm going to write my solubility product constant expression. But looking back up, and you can do this in any order, I just want to do this conversion first, right? When we define, right, any of our equilibrium concentrations or constants, they're always using these brackets. And remember, these brackets always mean molar concentration, right? Just as a little side note, right? Whatever it happens to be, Ka, Kb, Ksp, Kc, Kp, we have a gazillion of them now, right? This is always going to be concentration of products over the concentration of reactants. And we need to remember that those brackets mean molar concentration, right? Molar concentration is just another way to say molarity. So my solubility needs to be converted to molarity. I can't leave it in grams per liter because my expression is defined as molarity. And you can write your equation out first if you want. I'm going to do the conversion first. So we do need to convert grams per liter, right, to molarity, which is moles per liter, right? Remember, molarity is moles per liter. So I don't really have to do anything with the bottom, right? It's going from liters to liters. I just have to convert from grams to moles. We haven't done a lot of that this semester, but that should be something that you're pretty good at. How do we convert between grams and moles, right? It's the only way we ever convert between grams and moles and grams. Yeah, hopefully you guys are saying molar mass, right? If you have grams and you need to get moles, or vice versa, have the arrow going in both directions, molar mass is always going to be how we do that, right? Our units on molar mass are grams over moles, so we use it to convert between grams and moles. So I do need to figure out the molar mass of calcium fluoride, right? Calcium fluoride is CaF2. So I'm grabbing my periodic table and my calculator. Sorry for the shuffling noise. So I usually round my molar masses to 2 digits after the decimal point. So on the periodic table, it's 40.078. I usually round that to 40.08. If you want to carry them all out, that's fine. Just don't carry out less than 2 digits after the decimal point, unless of course there isn't any more than that. So you can do them all if you want, just don't do less than 2. So when I figure out my molar mass for calcium fluoride, I get 78.08 grams per mole. So if I take this number, right, 0.016 grams per liter, and then since grams are on top, I need grams to go away. I need to have my molar mass on the bottom. And then these units are going to cancel. I'm going to be left with moles per liter, which is molarity. So calculator again. And I get that my molar solubility is 2.0 times 10 to the -4th molar. So that's the number that we're going to start with when we try to figure out our concentrations of calcium and fluoride. So essentially, if we were to compare this example to the last example, this number is to calcium fluoride, what this number is to silver chromate. So this is my molar solubility. So now I can write my equation. It is solid. I'm going to get 1 calcium and 2 fluoride ions. If this is 2.0 times 10 to the -4th molar, so is this one, right? Because it's a 1-to-1 ratio. For every one of these, there's one of these. And then fluoride is going to be 2 times that, which is 4.0 times 10 to the -4th molar. Right, and we're multiplying it by 2 because it's a 1-to-2 ratio, right? If you wanted to set it up using dimensional analysis, right, stoichiometry, for every 1 mole of this, there's 2 moles of this. I know that my expression is going to be my concentration of calcium raised to the 1st power multiplied by my concentration of fluoride ions raised to the 2nd power. Plugging those numbers in. Don't forget to square your concentration of fluoride. And then I'm grabbing my calculator again. And I got 3.2 times 10 to the negative 11th. And please be typing these in also. I want to make sure that you can type it in scientific notation and then square it and get the right answer. So please, be sure to hit pause if I'm going too fast. Get out your calculators, type these numbers in, and make sure you can get the same answer as me. Again, we might be off with a little bit of rounding, that sort of thing, if you're keeping everything in your calculator from one step to the other or just rounding after each step. But that's what we would get for this one. I know I had said we were going to do one more example, but I lied to you. I want to do one more example. So this one, again, just another little twist on it. So if my concentration of fluoride ions at equilibrium is 0.0236 molar, what is the solubility product constant of lead to bromide? Remember, lead is one of those variable charge metals, so when you're writing the name, you do need to have that Roman numeral. So lead to bromide. So I always like to start again by writing my equation. Unless you're given like gram solubility in that last one, you need to convert it to moles, then the order that you do that in doesn't really matter. This is a solid. If you look at your solubility rules on the front of your periodic table, rule 3 tells us that bromide ions tend to be soluble, or compounds with bromide ions in them tend to be soluble, but lead 2 is an exception to that. So this is solid. It's going to form lead 2 plus 2 bromide ions. And it's telling us that at equilibrium, my concentration of bromide is 0.0236 molar. And then we do need to get our concentration of lead, right? We need to be able to plug these into our expression, right? My solubility product constant is equal to the concentration of lead 2 plus multiplied by the concentration of bromide ions squared, and we have this number, right, 0.0236 squared, that's given to us in the problem, but we need to figure out what this concentration is. And this time, again, I'm just going to use that ratio. I know that for every 2 of these, there's only 1 of these. So I know that at equilibrium, my concentration of lead 2 plus is going to be half the concentration of my bromide ions. So 0.0236 molar divided by 2, that's what that number is going to be equal to. So I'm just grabbing my calculator here real quick. And I get that to be 0.0118 molar, right? And again, I'm just using these ratios. You can put the 1 here if it helps, right? For every 2 of these, I only have 1 of these. So my concentration of lead is going to be half my concentration of bromide. So going back and plugging that number in, and then doing the math. I get 6.57 times 10 to the negative 6 for my value.